what we've got over the last year or so here are some interesting improvements and developments with PowerFlex, software-defined storage and infrastructure. So today I'm going to really focus on the enterprise file support, the NVMe over TCP connectivity, our new unified management structure, and I want to get at the end to talking about our cloud deployment. Earlier in the year, Dell announced Project Alpine, this initiative to bring software-defined storage into public clouds. PowerFlex into AWS is that first fruits of that adventure, and we'll talk about why that was so straightforward. I'm gonna skip over these bottom ones for time, but basically, you know, in the latest releases, there's always iterations on network path resiliency improvements, new replication topology things. I think the last time we were here at Tech Field Day stuff, we talked about the replication additions in PowerFlex and, you know, increased node densities and so forth. But what I want to do is give, like, I don't know how many people are familiar with PowerFlex's architecture, how it lays out something like a 5-minute fast overview here and rush through it. So basically, think of PowerFlex as a software-first architecture, right? Scott mentioned this earlier. It's designed to be as agnostic as possible to the underlying hardware in the beginning. So really, we just need a bunch of x86 nodes in networking and a few pieces of software to make it work, right? We need a piece of software to do the supplying of storage. We need a piece of software to consume the storage, and we have some software to do the metadata management of the cluster. That's like a little highly available cluster within the cluster that supervises those operations, does all the rebuilds and so forth. I'm not going to really talk about that today. It's just in the background.
The SDS was Scale I/O originally, correct?
Well, the whole thing was, okay, right? And so those fundamental features were there in the beginning, and the basic architectural principles are still the same. So what do we need to do? So the first part's pretty common, right? You install the SDS onto some nodes that have storage in them. Those, you know, extract the volumes or abstract the volumes out of the nodes and then form a virtual storage pool out of the whole thing. That's pretty typical. What's not necessarily typical is that the performance characteristics of that storage pool are the aggregate of the capacity of all those drives, but also the performance of each of those nodes that are contributing to that storage pool. So as you expand it, everything gets faster as well as bigger. Carve out volumes, map it over the network. We run only over an Ethernet fabric to the client, which presents it to apps and things. The interesting part's here, right? So when a SDC, the storage data client, gets a volume, right, it's given by that metadata manager cluster a small map of where the address space of that volume is distributed across all of the contributing SDSs in the system, right? So very lightweight little piece of information to know how to make read and write requests to different parts of the system, because we're going to spread the data in that volume evenly across all the contributing pieces. That gives us this massively parallel processing inside the system for great performance. So already talked about installing the SDS to create a storage node. So from a PowerFlex perspective, the character of a node is primarily determined by the software we've installed on it, right? Obviously, if you install the SDS piece of software on a node that doesn't really have any data disks in it, it's not going to be useful, but that's what makes it a storage node for us, is you install the SDS on there. Same thing for compute. The only thing that makes it a compute node is we install that storage data client. And then if we go ahead and install both of them onto the same node, we actually end up in hyperconverged world from our perspective, right? Where that particular node is a part of the cluster, both contributing and consuming storage from it. And that's true whether that's a hypervisor or just a bare metal Linux OS or whatever. Okay, we're indifferent to that. All right, so this lets you create architectures in your data center however you want. If you want to separate the compute and storage, go ahead and set it up that way. Like put them on different boxes, different nodes. If you want to go very dense, have a single scaling block for dense scaling, put them all in a hyperconversion mode. But if you wish, you can mix it up and on the fly and have some that are contributing storage, some that are consuming storage, and some that are doing both jobs, and they all can talk to one another. So we try to keep that as, like I said, as abstracted away from the details of the hardware as we can. So we talked about how we create this sort of peer-to-peer mesh between the storage data client and all those SDSs that will ultimately host the data. We do that throughout the system, right? It's a peer-to-peer mesh across all the pieces. And what you can't see on the slide here is that there's a similar pattern but among the SDSs themselves, and that's a part of what creates our data resiliency layer, as we can sort of move, rebuild data back and forth as if we lose a piece of hardware or something. So, building blocks, okay? That's the general architecture, that's the structure of it, how we get extreme scale in the system, and how we linearly increase performance along with that scale. But what do we do when we want to add new things, right? Well, we introduce a new piece of software, right? The first three were fundamental pieces. We can start adding optional pieces of software into the system that you can install to get new functionality. So again, a couple of years ago, we introduced the storage data replicator, which sits inside the system and handles those replication activities between two peered systems. And now with 4.0 release this year, in 4.0 we can have up to 5 peers in any arbitrary topology. But what we've done now is introduce the storage data target, which is our sort of, think of it as a translator of the NVMe protocol into the PowerFlex backend. All right, so that supports the discovery services and the host connections and so on. To show the difference between, like, this is the earlier architecture, right? You've got your storage contributing nodes on the bottom. You've got, say, in this case, ESXi on the top, which has that SDC installed into it, which then maps the volumes we create, gets consumed by the VMs, or if you want to build data stores or so forth. Now what we're doing is we introduce this storage data target, which sits and is installed alongside the SDS on all these nodes, and does this translation protocol between NVMe from the initiators, and then has that sort of same logic as the SDC inside it to be able to speak over this internal mesh to all the SDSs in the back end. Okay, couple of differences. So with the NVMe initiators, right, it's only going to connect by default to 4 of the SDTs. Sort of the protocol itself has some limitations in how many targets it can be talking to simultaneously. Remember, if I've got, say, 32 SDS nodes in the system, my SDC would be talking to all 32 simultaneously. In this case, by default, it'll talk to 4. You can bump it up to 8 if you wanted to, and then those will actually talk to the back end. So, you know, the NVMe over TCP protocol is very lightweight, it's very fast, but from a scalability perspective and performance at this point, the PowerFlex SDC on that same Ethernet fabric is still has an edge, right? It's still more scalable. It has that sort of dynamic built-in multipathing all on its own, and it's still about 20% or so more performant than the NVMe. Now, NVMe over TCP is beginning. It's building and growing, so as that architecture evolves and as things get introduced, then we'll, of course, be implementing those and rolling those into the system. So we'll see how that moves.
So in that case, there's no SDC running in the host layers?
No, because so one of the advantages of being able to have NVMe over TCP as your protocol layer is that you're not obligated to install anything on the host itself. So some customers don't want to install an SDC into the kernel on their hypervisor, and in that case, this is the way to go, right? You still can have that performance scalable storage in the back end from PowerFlex. You just have a new method of consuming it. Now, you could install both. If you had a case for it,
protocols.
You could. Now, a single volume can only be shared over one or the other, but you could have volumes on the hosts that some come in from NVMe over TCP, some come in over the standard SDC.
I guess the critical question from my perspective, NVMe TCP is intended to be, extremely rapid, low latency performance. By having this translation layer sitting in the storage nodes, I guess I'd call them, aren't you adding additional overhead?
Yes. There's one extra hop in there, right? Because your data path is coming from the ESXi host into that, and then we have to go and talk to the rest of the system. But part of the reason we do PowerFlex architecture the way it does, we have to be able to keep or maintain these really large scalability profiles, right, for our customers, so that we continue to maintain that linear scalability in the system. We don't violate those architectural principles when we introduce a new technology or piece of software. There are future options for improvements and changes. Again, the protocol is going to change. How we implement it may shift a little bit, but that's part of the reason why, even though it's an efficient protocol, it's still not quite as powerful as the SDC right now.
So in this case, it can only attach the host can only attach to 4 8 targets, but in reality, you could have 256
Storage nodes in the back
sitting
end.
on the back end.
Exactly, right. And providing all the sort of capacity and scalability and power. And we can keep building that on the fly.
And
So that dynamic character is still
performance
maintained.
aggregates across
Yes.
all the storage nodes.
Right. There's just one extra hop on the data path. That actually plays into the next design here. A similar idea that we can scale out the storage layer while having a NAS file layer sitting in front of it. We abstract away the compute in the NAS on the front end from the storage on the background as we implemented file services now into PowerFlex. So the NAS technology, right, is, as Scott mentioned earlier, it's one of these sort of common portfolio-wide structures, right? So the underlying technology for the file services that we are implementing in PowerFlex now is mostly exactly the same as in PowerMax and PowerStore, right? So we're sharing certain resources. How it gets implemented in each of these storage systems will be a little different, right? But so all the features, the protocols supported, the NFS, SMB, so on, those are all going to be the same, right? It's just how the storage backend gets implemented is a little differently. So what we're doing here is we're basically putting new physical nodes in front of the system, right, that has the SDC in it, which can talk to the back end. File systems are just volumes in PowerFlex. They just get mapped through that SDC into, well, I've listed the NAS container on here, but that's just a piece of software which hosts the NAS servers, right? Those are the ones that have the different namespaces, have all the different security profiles, and can be individuated for any of the consuming application hosts that want to grab them, right? So you can have up to 128 of those on any given node, right? And then each of those can have up to 256 file systems associated with it. So, what we can have between 2 and 16 of those physical controllers for the NAS head front ends in front of PowerFlex, providing file services to clients. So, they function from the client perspective. You can see there's 2 lines there. They function as basically like an active-passive front end. So it thinks that way. But in the back end, of course, it's just a container sitting there, and then the PowerFlex can migrate volumes and move them around. So if there's a problem with one of these as the, say, primary or the secondary for the client, we could always move it over to another one, right? So that there's flexibility in there as to how it gets consumed from PowerFlex to the client. But from the client's perspective, it just sees its primary and there's a secondary to it.
Brian, there's and I'm not sure what the terminology is, but there's a file services NVMe level protocol. I think it's like NVMe over file kind of thing. It's an RDMA solution kind of thing. Do you have support for that in your NAS container, or?
No, not this time. No. And the thing is, as far as like the network transports go, like other than the NVMe over TCP implementation, we're just sticking to TCP/IP networking, right? Because all the PowerFlex protocol stuff runs over TCP/IP. Real quick on unification. So if anybody had experience with PowerFlex in the past, they would know pre-FART 4.0 management, there were several different user interfaces you had to go to do things. Part of it's just the history of how this product evolved, right? But you might have to go to the PowerFlex UI itself to do day-to-day management of volumes and operations. You'd have to go to PowerFlex Manager to do lifecycle management of the hardware, because although up until now, of course, we've been talking about software only characteristics, we do have to run it on some hardware somewhere, and we do sell, PowerEdge-based appliances that run the software. But with 4.0, we actually came up with a whole new unified management stack. And similar to what was done with PowerStore, this is a containerized management stack. It can be implemented in a few different ways. What I've characterized here is like you've got some kind of a hypervisor, in this case ESXi, on top of which are running some management VMs, which host this distributed Kubernetes cluster. In this case, it is a Kubernetes cluster. That have pods containers that contain all the different services and functions for PowerFlex at all different layers of operation, whether that's lifecycling hardware and networking, maintaining and upgrading the software layers, or just day-to-day operations of block or file. Okay, and then through standard ingress load balancer, we're presenting that to the UIs. We've got the REST APIs and different CLI interfaces. So that's just something that for us has been a necessary evolution as we go through the process of kind of unifying our M&O stack. But similar to what Jody was saying earlier, because we've got this containerized stack now, we're able to sort of improve, adapt, and bring in different pieces as we go.
And the containerization only applies to PowerFlex Manager, is that?
It's just the management stack, right? It's just the M&O stack. The ways in which we've always installed the software to the different either operating systems or hypervisors still applies. And what I really want to get to is PowerFlex on AWS. Because this is a software-first architecture, because it's pretty much abstracted away from the particular x86 architecture on which it's running, it was a pretty simple, straightforward stretch to bring this to the cloud services. So what we're doing is utilizing EC2 instances for the compute, okay? And then either using the attached instance store disks or sort of more commodity grade EBS in the background behind it. Same as before with on-premises, on-prem architectures, you scale it by federating instances, right? You bring more in, you get more power. You get more capacity, you get more performance. There's no performance limitations or only penalties for building it out like this. We do give you some choice on the instances to configure. We have a wizard tool that will basically walk you through, and we've pre-picked a set of them that are a best cost to performance set of balances and that we know work well. And we'll talk here in a minute about how we do something unique in protecting across availability zones in AWS. So I mentioned a second ago that you can either choose elastic block storage or the local instance store that comes with it, an instance. Use cases will determine how you go, and we can give you advice on this. EBS is, of course, persistent by itself. If you power down the cluster and you had data on there, it will still be on those EBS volumes when you bring it back up. But we're using sort of lower performance GP3 EBS volumes, and then of course aggregating them, federating them with our technology to create stuff that each individual EBS could maybe go to 16,000 IOPS. We can federate them into a large thing. You can do millions, right? Or you can use the NVMe backed instance store attached to them. Those are not persistent. So you'd have to use, say, the data domain virtual edition integrations and back it up to S3 if you're going to power down the cluster. Performance, same in the cloud as on premises, right? You keep adding, you keep growing. So basically here we've built up to 128 node cluster in AWS, and we've got over 31 million IOPS in the cloud out of a single cluster, or over 6 terabit per second of throughput. So you can't quite see it. There is a slight curve in those lines. It's not exactly linear, but it's very close.
How does that compare to on-premises with 128 node? I mean, you'd have to have similar compute, I guess.
Similar CPU and other and network, topology infrastructure pieces, but yeah, it's going to be similar. And of course, what numbers you get out of a cluster will differ depending on the hardware you throw at it. So they do vary, but the point is also that it is linear and it does just keep growing as you keep adding pieces. So of course, again, PowerFlex creates this distributed mesh. It slices up everything across these volumes. If we lose a volume, or if we lose a disk inside something or one of those EC2 instances, we just go through the process of doing our rebuild really quickly, and we're back continuing running. There's no disruption. It's fast, right? So these are another set of EC2 or AWS-based tests. You can see that in this case, it's 18 terabytes of data we're protecting. And at 8 nodes, it takes 20 minutes. It does take a while, but as soon as you get up into higher node counts in your cluster, you're down in the 2-3 minute range to reprotect the data. And it's important that we protect the data. We don't care about the devices. It's designed to be we don't care. Once the data is reprotected, more things can keep failing, and we don't care.
And maybe a question. Does PowerFlex require all the nodes to have similar storage devices?
Technically, no, but it's going to work best for you if you
So the
keep things.
performance numbers you're showing were with NVMe?
They were at the first that
Yeah.
instant store side.
There's a question also for me. How much time does it pass between, the node failure and the rebuilding process to start? Because if you have a node that goes on and off all the time, I mean, there is network connectivity issues or whatever, you don't want to start a rebuild and then find that, the node is back after like 2 minutes or 1 minute.
Right. Okay. So if it's a case of something flapping on and off, on and off, on and off, there's other mechanisms in the software to start ignoring that, right? We're not going to keep trying to initiate rebuilds every time something comes back and forth. But in general, and it's the same on premises as in the cloud, if you lose a disk, if you lose a node, there's about 7 seconds until we've said, okay, there's a failure, there's a problem, we're going to remap where that data layout is across all the contributing pieces and initiate a rebuild. So we don't wait. Like as soon as we know there's a failure, we don't wait, we start the rebuild. That's how our architecture works. Let me just do one quick comment here about the resiliency. Instead of protecting at the node level, we can actually group these nodes into fault sets. That's a technology we've had for quite some time. But what this allows us to do is create this distributed mesh of block storage across availability zones as we place the fault sets into different availability zones. So we can actually, you can lose connectivity to whole AZ, and actually we'll just do the rebuild and the rebalance of the data and your system's going to keep going. So that gives us something quite unprecedented, is a multi-AZ resilient block storage.
Really quick question. You had the i3 and 12X large. Is that the node that you have to use, or is that what your baseline is? That Amazon node type on the last slide, you had the i3.
Sure. No, we give you a set of choices, right? You can technically install it on anything, but our wizard tool that we kind of built up as sort of a preview into where things are going to go with, say, Project Alpine, does have certain node types from which we want you to select.
And it's EBS in the back end too, correct? You're using EBS for the disks for that.
You can choose whether to use EBS or the attached instance store.
I mean, that's ephemeral though, those.
Well, we have our own data protection scheme, of course.
Right.
And if you need to power down the cluster or something, we do have integration into data domain virtual edition. So we've already got white papers and architectures for this. So you could actually, we've got native asynchronous replication. We didn't cover it today. You can do then DR from on-prem to cloud. And you can also do it from cloud region to cloud region. And in the cases where you want backup to, say, S3, we can use the DDVE integration architecture and do that. So you could have instant store back things, power them down, but still keep your data and then restore.
I was just asking because that particular instance type that you brought up there it's like $100,000 for 3 years each node before storage, right? So
Right.
It does end up adding.
It will end up adding, but part of the ability to bring these up and down quickly, it takes about 20 minutes to deploy an entire cluster. It's very fast, it's scripted and automated.